Now that we've worked through our examples, we want to consider the case where we want to find absolute extrema. Now, we're only guaranteed to find absolute extrema if we have a closed bounded region. So we need to define more clearly what we mean by closed bounded region. In Calculus 1, we said the interval had to be closed. So I could go from closed A to closed B, like square bracket 1 to square bracket 5. Then I could find a critical point between open 1 and open 5, but I also had to check the value of the function at 1 and at 5, because those could also be places where the absolute maximum and absolute minimum over the closed interval occur. In a two-dimensional domain, we're no longer looking at the real number line, so we won't have a left endpoint and a right endpoint to check. Instead, we have a region, a subset of R2. If it's open, the region does not include its boundary, and we represent that with a dashed line. If it's closed, we make the boundary of it a solid line, like a solid black curve. So if you're looking at this region here, the one on the left is an open region, and the one on the right is a closed region. An open region is analogous to an open interval, open 1, round parentheses, to open 5, round parentheses, or negative infinity to infinity. A closed region is analogous to a closed interval, square bracket 1 to square bracket 5. As you might expect, since in Calculus 1, we had to check at critical points of the interior, open 1 to 5, and at the boundaries of the closed interval at 1 and at 5, that we're going to have to be looking for absolute maximum values at critical points on the inside of the region and also along the boundary. But there are infinitely many points along the boundary. I won't just have two z values to find as we did in Calculus 1 in a function of a single variable. Instead, there are infinitely many places to look. So what I'm going to have to do is somehow parameterize the boundary so that I can get it written in terms of a single variable and apply the rules from Calculus 1 to locate any minima or maxima along the boundary. Those places, those critical values, will become places to check for absolute extrema on a function of two variables on a closed region. Let's also define what we call by bounded. Bounded is a little bit different from open and closed. Bounded means that it can be completely contained within a disk. And for disk, read circle. I can draw a circle around the region on the left. Now, the radius might have to be very large. It could be 10 billion miles. It doesn't matter. That's still finite area. If it's a bounded region, it's contained within a circle with finite area. If it's an unbounded region, you can't contain it within a circle of finite area. This would be like the region that we have on the right. On the right, you can see that that region is the space that is above the decreasing line and to the right of the other decreasing line, the steeper one. When we're looking at that, that region continues forever out and up. It will include eventually much of quadrant 1, quadrants 2, and quadrants 4. All right. It's not a bounded region. I can't draw a circle that would contain all the points in that region. We need an extreme value theorem for a function of two variables. The extreme value theorem says take a continuous function f on a closed and bounded set D. So I not only need a closed region, including the boundaries, but it has to be bounded, right? Technically, negative infinity to infinity is both open and closed. All right, so we consider it both an open set and a closed set. But when you're talking about a bounded region, no direction can go to infinity. As long as I have a closed bounded set, closed bounded region in R2, then the function has to have both an absolute maximum z value in that set and an absolute minimum z value in that set. Now, D could be the domain of the function, but more likely it's a subset of the domain of the function in the xy plane. In other words, we're guaranteed to have a highest point and a lowest point if our region is both closed and bounded. Unfortunately, this is an existence theorem. It tells us that the absolute extrema have to exist, but it does not tell us how to go about finding them. All right, so we're going to have to use some of the techniques we've already learned in order to find them. When you think about a boundary in R2, we'll typically be working with line segments, circles, arcs, parts of ellipses, things like that we've worked with before. Here are some locations for absolute extrema on a closed bounded region, either at the critical points of the inside or at any value of the function on the boundary. But the boundary has infinitely many points, so what we're going to have to do is use our calculus 1 techniques and our calculus 3 techniques to parameterize the boundary in terms of one variable, then apply calculus 1 techniques to find the critical points on the boundary. Here are the steps to finding absolute extrema. Suppose that you have a function of 2 independent variables and the function is continuous on a closed bounded region D, and assume that the function is differentiable. We need differentiability in order to find the critical points. To find the absolute maximum and absolute minimum values of the function, the surface on that region out of the domain, first we find the critical points of the surface within that region. If you find a critical point, but it's not within that closed bounded region, it's not one of the ones you're looking for, so you just discard it. You're going to calculate the function value at each of the critical points. In other words, you're going to substitute them into the equation for z and get a z value. You're going to then determine the maximum and minimum values of the function on the boundary using calculus 1 techniques after parameterizing the boundary to be a function of one variable. Then you're going to look at all the z values for all of these different points and pick the biggest one. That will be the absolute maximum. Pick the smallest one, and it will be the absolute minimum. Now, finding the maximum and minimum values of the function on the boundary of a region that's closed and bounded can be really challenging and quite difficult. We're going to work through 2 examples in this lecture. There is another method, but it is also difficult, and your course may or may not cover it. In general, it's called the Lagrange multiplier method. The Lagrange multiplier method says that if the set D is a rather complicated curve, and we're looking at it and we have first order partial derivatives of G exist, and we're setting it by some function G as a function of xy equal to a constant, then we can use the method of Lagrange multipliers to help find the extrema of the functions on the boundary. This is covered in section 4.8 out of the textbook, which again may or may not be covered in your course. Let's take a look now at example 6, which is our first example on how we're going to find these critical points on the interior and on the boundary. Example 6 has the function 4x squared minus 2xy plus 6y squared minus 8x plus 2y plus 3, which is a quadratic surface. However, we want to find the absolute extrema on a restricted domain. The domain of the actual surface is the entire xy plane, all of R2. We want to find the absolute extrema on a very restricted part of that domain. Basically, for x between 0 and 2, including 0 and 2, and y between -1 and 3, including -1 and 3. If you think about it, this sort of makes sense in the real world. There are lots of times when we model a situation with a function, but because of manufacturing processes, we know that only a small subset of those values would actually work in the real world situation. In other words, we're restricting the domain. In this case, the restricted domain corresponds to a rectangle in the xy plane, where x goes between 0 and 2 and includes the edges, and y goes between -1 and 3 and includes the edges. I'm interested in finding the critical points of the interior, which I can find by applying the steps that we've done previously to the original function and making sure that they fall within this purple shaded area. Then I will have to parameterize each line segment separately, unfortunately, and find the critical points for each of those. Let's go ahead and start with the critical points on the interior. In order to find the critical points, find where the first partial derivatives are both 0. Pause the video now to work it out, then turn it back on to check your work. The first partial with respect to x is 8x minus 2y minus 8, and I set it to equal 0. The first partial with respect to y is negative 2x plus 12y plus 2, also set to be 0. I took the partial with respect to x and solved for y to get y equals 4x minus 4. I substituted that expression into the first partial with respect to y and found that x equals 1. Substituting back into the expression for y, I get that the y value is 0. So my critical value, my critical point from the domain is the ordered pair 1, 0. Now let's take a look at the boundary. Finding the critical points of the interior is generally pretty straightforward. The only thing we need to check is to make sure 1, 0 falls within the purple rectangle. And 1, 0 would be located here, which is definitely within my rectangle. The next thing I want to do is I want to consider the boundary, which are the darker purple lines. The idea in this case is to take each line segment and parameterize it. I want to write x as a function of t and y as a function of t on each of the 4 individual line segments. If I can write x in terms of t only and y in terms of the same t only, then I can rewrite the original equation in terms of t only. So instead of being a function of x and y, g would just be a function of t. That turns it into a calculus 1 problem, where finding the critical points is much easier. Let's talk about ways to parameterize these lines. One of the ways that we can parameterize the lines is simply to label them, as I did. I called them L1 for the lower horizontal, and then moving counterclockwise, L2 for the right, L3 for the top, and L4 for the left. Line 1, line 2, line 3, line 4. How can we parameterize line 1? There are infinitely many ways to parameterize that little section there. But one of the things that you can realize is that, well, the y value along the lower segment here is always -1. The y value never changes. It's only x that depends on something else. In this case, we want x to depend upon t. So to parameterize the first line segment, one of the easiest ways to do it is simply to let x be t and let y be -1, with the restriction that x only varies between 0 and 2. That will force y to be -1 and x to vary from 0 to 2, but x equal t. Now, there are infinitely many ways to do this, and we studied this in an earlier chapter where we found ways to parameterize line segments between 2 points where t always went between 0 and 1. Here, t will go between 0 and 2, but we don't need it to go between 0 and 1. My advice is to choose the easiest parameterization you can find. In this case, I'm going to let x be t and y be -1. Now I want to rewrite the original function, which was in terms of x and y, in terms of only the parameter t. Go ahead and pause the video while you replace every x variable with t and every y variable with -1. When you have your answer, g is a function of t, turn it back on. So, did you come up with a function of t of 4t squared minus 6t plus 7? That's what you get when you replace all the x variables with t and the y variables with -1. Remember that because x is restricted to go between 0 and 2, then t is also restricted to go between 0 and 2. Now we want to apply our Calculus 1 techniques to find points at which we need to check to see if we have an absolute extrema on the surface. Since this is now a function of one variable, but over a closed interval, I definitely need to check at 0 and 2. But this would be at 0 and 2 for the x value. If x is 0 and y is -1, then this is giving me that left corner that you see there. If I check the right endpoint where x is 2, y is again -1, which is giving me a corner. But that should make sense to you from Calculus 1, because in Calculus 1, corners are places where the first derivative doesn't exist. I would need to check it anyway. So I've got 2 points here, 1 point from before in my critical points, and now I need to find what points along this line segment might be a critical value. So I take my function g of t and I look for the critical points of that function. Again, notice that it's defined everywhere for all values of t, even though we're only interested in between 0 and 2. To find the critical values, find where the first derivative equals 0. Where is g prime of t equal to 0? Well, take the derivative, 8t minus 6, set it equal to 0 and solve. 8t equals 6, or t is equal to 3 divided by 4. This gives me yet another point that I need to check. This gives me the ordered pair 3/4, comma, -1, because on this line segment, the y value is always -1. So I'm checking this point here, and I got another point earlier here. These are the points so far that I have to check to see if they have the maximum z value or the minimum z value. Now that you've seen the process, repeat the process on each of the 3 other line segments, then turn the video back on so we can compare our work. Let's see how you did on parameterizing line 2. Line 2 is the part that extends from the ordered pair 2, -1 to 2, 3. That means we need to check those corners. We've already marked that we need to check 2, -1, but we need to add 2, 3 to our list of points to check. Remember, this is because y is now being restricted in a closed bounded region. And for a function of a single variable, we could find extrema at the endpoints or critical point of the interior. Then we need to find the critical points of the interior. To parameterize line 2, since y is changing, but x is always 2, we let x be 2, but y be t, and allow y to vary from -1 to 3. Replacing x with 2 and y with t in the original equation of the function, we get g of t equivalent to the function f as 6t squared minus 2t plus 3. To find the critical points, we need to find where the first derivative is 0 or not defined, but the function is defined. The function is defined everywhere for all values of t, but here we're only interested in the values between -1 and 3. We take the first derivative to get 12t minus 2 and set it to 0. That gives us a t value of 1/6, and in this case, y is t, so y is 1/6. But on this line segment, x is always 2, so we have the ordered pair 2, 1/6. That means that we now have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 places we'll have to check. Let's move on to line segment 3, which is along the top edge. On line segment 3, the y value is constant. It's always 3, but x is varying between 0 and 2. In this case, we can let x vary from 0 to 2. Note that we need to add another point to check on the corner when we have 0, 3. That's because x is defined on a closed bounded region. So by the extreme value theorem in calculus 1, for a function of a single variable, we need to check the endpoints. When we replace x with t and y with 3, we get the function 4t squared minus 14t plus 63. Take the derivative to get 8t minus 14. The derivative is always defined, so set it equal to 0 to find the critical point, t equals 7/4. Since in this case t is representing x, our x coordinate is 7/4 and y is the constant 3. This gives us yet another critical point at 7/4, 3. And that would be at, I think, about here, all right? Which now gives us 1, 2, 3, 4, 5, 6, 7, 8 places we need to check. Let's now move on to line segment 4. Line segment 4 is the far left side. When we're looking at the far left side, y is varying between -1 and 3, which is a closed interval, but we've already marked both of those points as places to check. We will also now have x being constantly 0. So when we replace x with 0 and y with t, we get the expression for g of t, 6t squared plus 2t plus 3. We take the derivative and we get 12t plus 2 is 0. It's always defined, so set it equal to 0 and solve. When you set it equal to 0 and solve, you get t is -1/6. On this line segment, y was equal to t, so the y coordinate is -1/6 and the x coordinate is 0. Now that we've parameterized the entire boundary and found critical points at places in the corners, which were the endpoints of our closed intervals, and on the interiors, let's put all these points together and try to find out where our maximum value is. I think, if I can remember right, that we have a point here, a point here, a point here, here. I've forgotten where that one goes. There's one down here. I think it's here. There's one here. There's one here, and I just got 0, -1/6, which would be about here. All right. Let's go ahead now and create a table to keep track of all of this information. In the table, we can classify the different places to look for an absolute maximum or absolute minimum on the surface. Remember to start with the critical points of the interior. We only found one of those. That was that 1, 0. Find the critical points of the boundary line segments, which was 3/4 -1, 2 1/6, 7/4 3, and 0 -1/6. Then there were 4 corners to the regions, which gave us the endpoints of the closed bounded intervals where our line segments were defined: 0 -1, 2 -1, 2 3, and 0 3. Take each of those ordered pairs and substitute their x and y coordinates into the definition of the function to find the z value at that location. I've already done the work and written it down for you in blue. The value of z at 1, 0 is -1, which is the smallest number in our list. That makes this value right here the absolute minimum, which is -1. And it occurs at the point on the surface 1, 0, -1. So I have an absolute minimum of -1 at 1, 0, -1. Let's now take a look at the largest z value that we were able to find. The largest one out of all the values is 63, which was found at a corner, 0, 3. This makes this the absolute maximum. So we have an absolute maximum of 63, and it occurs at the point, and I need to scroll up a little bit so we can see all of it, at the ordered triple 0, 3, 63. That value you're getting is the z value. Let's now take a look at this particular surface on CalcPlot 3D and see if our solutions make any sense. When you plot the region, you want to make sure that you restrict the domain. You can do that by clicking on the gear symbol, and in these boxes for x and y, you can enter your restrictions. X is between 0 and 2, and y is between -1 and 3. Make sure to hit enter so you can see the restricted surface you're looking at. To me, this kind of looks like, well, it looks like a bucket seat in a car, right? Or maybe a porch swing seat where it kind of dips lower here at the bottom and then has a curved back going up. If you're looking at this, you can tell that there is going to be something down here at the bottom, and it looks like I have a maximum up here. Remember that if you're on a closed bounded region, you're guaranteed to have an absolute minimum and an absolute maximum. And we found those values previously. Our absolute maximum, I believe, was 63, occurring at that point right there, which I have graphed if I take the other menu off, at 0, 3, 63. And I have the absolute minimum at 1, 0, -1. Now, what about the restricted domain? How can I be sure that I have the restricted domain? Go ahead and click on 2D. Well, let's turn it first so you can see kind of what it looks like. It took a little finagling with the values for X, Y, and Z on the scale to get a decent picture of what this one looks like. Now let's look at the 2D picture. Use your mouse wheel to be able to see the entire thing. Do you notice now that the X value is from 0 to 2 and Y is from -1 to 3? This is the rectangle that we were computing the absolute extrema on. Notice also that we have an absolute maximum up here at the corner, and we had our absolute minimum at the critical point of the interior. Now that we've completed one example, let's try another one where the boundary is not line segments, but is instead a circle. We want to take a look now at example 7. In example 7, we want to find the absolute extrema of the function 2x squared minus y squared plus 6y on a disk of radius 4 given by the equation x squared plus y squared is less than or equal to 16. Less than or equal to means that it includes the boundary. That makes it a closed region. And since it obviously can be fit into any circle of radius larger than 4, it is bounded. In this case, we're going to want to find the critical points that fit within this space. So their x value will have to fall within this circle and y value as well. Then we're going to have to parameterize the boundary curve somehow so that we can find any critical values along the boundary curve. Let's go ahead now and take a look at finding the critical points. To find the critical points inside the disk, the first thing you want to do is solve the system where the partial derivative with respect to x and the partial derivative with respect to y are both 0. Go ahead and pause the video now to work that out. So let's see how you did. When we're looking at this one, the first thing that we can do is find the partial derivative with respect to x. In this case, we're going to set it equal to 0. The partial derivative is 4x. When I set it to 0, that tells me that x is 0. The partial derivative with respect to y is negative 2y plus 6, which I set to equal 0, and I get y equal 3. This gives me one critical value, the ordered pair 0, 3. This is the point on the interior of the circle where I need to look to see if I have an absolute maximum or minimum for the z value. The next thing I need to do is parameterize the boundary. The boundary is given by the circle x squared plus y squared equals 16. And my function is 2x squared minus y squared plus 6y. When I think about the function itself, the function has an x squared term and a y squared term, but no x term. It does, however, have a y term. So when I'm looking at this one, the easiest way to parameterize it is to choose the unsquared variable. In other words, choose y to be the parameter. Once you know y is the parameter, you can solve for x, or in our case, we really only need x squared since that's all that's in the function. Remember, we're wanting to stay on that circle, x squared plus y squared equals 16. So we look at the function itself to determine which variable might be a good choice for the parameter, and then we take that and substitute it into the circle. If I put it into the circle where x squared plus y squared equals 16, and I let y be t, then I have x squared plus t squared equals 16, or x squared equals 16 minus t squared. That gives us an expression in terms of only t to substitute for x squared. Go ahead and pause the video to replace x squared with 16 minus t squared and y with t. After you do that, go ahead and find the critical points on that function. Then turn the video back on and we'll check your work. When I'm looking at parameterizing that curve, I replaced y with t and x with 16 minus t squared coming from the circle that it is the boundary, x squared plus y squared equals 16. I substitute those into the function f in place of x and y. When I multiply it out, I get the equation in terms of t, negative 3t squared plus 6t plus 32. This is now a function of a single variable, so I need to find the critical values. To find the critical values, we take the first derivative. When I take the first derivative, I get negative 6t plus 6. This is defined everywhere, so there won't be any type 2s. I set it equal to 0 and solve, and I get t equals 1. But I originally set t to be the y value. So if y, which is t, is 1, and x squared is 16 minus y squared, or 16 minus t squared, then x squared is 16 minus 1 squared, so x squared is 15. That gives me two values for x for the same value of y equal 1. That gives me plus or minus the square root of 15. This gives me two critical points along the boundary, negative square root of 15, 1, and square root of 15, 1. But remember that when we're on that circle, we set y to be t. On the circle, since we rewrote our equation in terms of the parameter t, were there restrictions on the value of t or on the value of y? If we look back at our boundary, remember that it is a circle of radius 4. So y, which is our parameter t, has to be between negative 4 and 4. It's in a closed interval from negative 4 to 4. That means we need to check those values as well. When we do that, we're going to be adding a couple of points. We have to check the endpoints by the extreme value theorem from Calculus 1. When y is a negative 4, we take the equation x squared equals 16 minus y squared, and whether it's 4 or negative 4, when I square it, it becomes 16, which gives me that x squared is 0, or x is 0 in both cases. This gives me two additional places to check, 0, negative 4, and 0, 4. Now we want to create a table and gather all the information that we have and compute the z value at each of those critical points. In the table below, I have the critical points of the interior as 0, 3. The function value there, substituting into the original equation, gives me 9. I had two critical points on the boundary, negative square root of 15, 1, and square root of 15, 1. And I also have the endpoints of the bounded region, which I could also call, well, they're not really critical points of the circular boundary. They're endpoints, which gives us 0, negative 4, and 0, 4. Computing all of the z values for all of these critical points, I have a minimum value of negative 40. That makes negative 40 an absolute minimum. And that puts the minimum value of negative 40 at 0, negative 4, 40, which is kind of going off the page. Let me see if I can write it down below. 0, negative 4, 40. There we go. That is definitely my absolute minimum value. What's my maximum? Well, oddly enough, I get the same number twice, 35. 35 is the largest z value that I have, but it shows up twice. That's okay. You still only have one maximum z value, 35, but it occurs in two locations. So I do have an absolute maximum, which is equal to 35, but it occurs at two ordered pairs, at negative square root of 15, 1, and at square root of 15, 1. And that makes each of those the solution to this maximum minimum problem. Now let's take a look at this particular shape out on CalcPlot 3D. When we look at this shape, it's really an interesting kind of shape. It reminds me a lot of a Pringles potato chip, if you think about it, sort of. Again, you want to plot the function for z, click on the gear symbol, and make sure to restrict your x and y according to your boundary. In my case, the boundary is a circle of radius 4. So x is between -4 and 4, and y is between -4 and 4. Actually, it's a little bit more restricted than what I can show easily with CalcPlot 3D, because it's really supposed to be on a circle. And what this is giving me here is actually a rectangle. I'll show you in just a moment how to get the true shape of the restricted domain. You can see here that it does have two values, and I'm going to try to get it to be straight up and down if I can, and rotate it. There you go. And you can tell that the value on the left and the value on the right are at the same z value. That's my maximum 35. And this one down here at the bottom is my minimum. I think it was -40. Now, I said that the restricting the domain with the gear symbol isn't really doing what I'm supposed to be doing. That would actually give me a rectangle, but I wanted a circle. So what I really need is, well, a cylinder, which is the circle x squared plus y squared equals 16. So in the next image, you'll see this cylinder, which is cutting through the other shape. Let me make the cylinder a different color so we can see it a little bit better. When I click on the cylinder, let's make it a constant color, but still see-throughable, if that's even a word. And I'm going to use a BSP triangulated or not triangulated to smooth out the edges where they intersect. And I did that by clicking on, where'd it go? 3D mode. All right, so BSP tree, either triangulated or not triangulated, will smooth out the edges where they intersect. I'm taking this tube, like a toilet paper tube, and I'm cutting through this other surface. When I cut through the other surface, I only get the part in between. I'm getting the part that if you rotate it this way, I'm getting that part right there, cut out of the surface. And I'm trying to find the maximum z value and the minimum z value inside that circle. That's what I'm doing. This concludes the video lecture on this section 4.7, maxima and minima. In the next video lecture, we'll take a look at the Lagrange multiplier method. If this is not required for your course, simply move on to the next section out of chapter 5, where we start taking a look at double integrals. Join me soon for another video.